Geometry students, Mr. Zacek here. We're at our last lesson on the year, which is on indirect proofs. And you may or may not be aware that we have been um, doing direct proofs for throughout the course of this year, and kind of a small piece in this course would play a larger role in some other courses, but a small piece in this is indirect proof. And indirect proof are proofs by contradiction. So some of these first notes here come off of the Regents Prep website, and a great resource as you're getting ready for your finals and looking for some practice. And what we're going to do in an indirect proof is we're going to assume what we need to prove is false, and then show that a contradiction happens or something absurd, as it says. So um, the steps for that: assume the opposite, and this is a big thing here is what we've got for number one. Assume the opposite of what you are trying to prove is true. See what conclusions can be drawn, and search for a conclusion that you know is false. So here's what we want to do. We want to search for a conclusion that we know is false because it contradicts a given or known information. All right. A lot of times it's going to be a given. Then our assumption is going to lead us to a false conclusion. The assumption must be false. Okay, so for example, let me try to help you picture this kind of logic in another way. If you have a maze and let's see if I can draw a maze. It gives you kind of two options when you enter the maze. Okay. So this is where you enter, and this is where you exit. Okay. If you enter and you turn this way, and then you follow the maze here, do you get out? No, you don't. So what that says is you made the wrong turn. So you assumed that you were supposed to go, in that direction, but that was wrong. So the nice thing about um, proofs is things are either true or false. And so since our assumption leads to a false conclusion, the assumption must be false. So again, back to the maze example, because we tried this one way in the maze, well, that turn was the wrong turn, so therefore the other turn must be true. Okay, so you can kind of think of it in this way. It's either true or false. Well, that one was false, so the other one was true. And so how do we know when to use this? Um, Generally, when the word not or the presence of that symbol is when we're going to use this indirect method. So for example, like prove triangle ABC is not isosceles. Okay, that would be an indication that indication to use the indirect method. All right. When you have the not in there, that's when we're going to use it. So proof by contradiction, also known as reductio ad absurdum. I think that's how you say that, which Latin means reduce it to an absurdity. Okay. So, again, back to the maze. Well, we tried that way, it didn't work, so therefore we made the wrong turn here in the maze. All right, so here's an example, and this one's already done for you, but I just want you to kind of be able to think through it. In the accompanying diagram, ABCD is not isosceles, and you have altitude BD. prove that BD does not bisect AD. So again, I want you to see in this proof the word not. So we're trying to prove that something is not true. That's when you're going to use the indirect method. So use the indirect method. All right. So as we're looking at this, it's not isosceles, but we do have an altitude. Remember, altitudes form right angles. So we got a couple right angles. Um, and we've got a reflexive property. And that's about all we've got there. All right, now, here's how you work this out. Obviously, we start off with our given. ABC is not isosceles and altitude BD. That's given. Assume BD bisects AC. Now notice that we're going to assume the opposite of what we're trying to prove. So instead of where it says prove BD does not bisect AC, assume BD bisects AD. All right, and here's the new reason that you need to know. It's an assumption leading to a contradiction. So we're looking for something to contradict that. All right, so now we begin going about the proof. And probably one of the things that we could say is, well, if I can prove that ABC is isosceles, that's a contradiction. So statement three, AD is congruent to DC. All right, now based off of what we've done, AD is congruent to DC based off of our assumption. All right, so you got to get that. This is based off of the assumption. If a segment is a segment bisector, then it divides a segment into two congruent segments. All right, BD is perpendicular to AC. If a segment is an altitude of a triangle, then it is a line segment extending from any vertex perpendicular to the line containing the opposite side. We know after perpendicular that we say we have right angles. If two lines are perpendicular, then they form right angles. Then you say these angles are congruent. So we've got an angle pair congruent to an angle pair. Back here we've got a side congruent to a side. By the reflexive property, we have another side congruent to a side. And so those two triangles are congruent now by side angle side. Well, now that the triangles are congruent, we can say something about their parts. So AB and BC, 1, 2, 3, 1, 2, 3. Those are congruent, corresponding parts of congruent triangles. Statement 10, ABC, this big triangle, is isosceles. Why? Two of the sides are congruent. Well, wait a minute, that's a contradiction to our given. ABCD is not isosceles. Here we're proving that it is isosceles. But what was our proof built on? Well, it was all built off of this assumption that BD bisects AC. So therefore, we know that BD does not bisect AC, the contradiction in steps 1 and 10. All right? We took the wrong turn in the maze back here in step 2. And a result of taking the wrong turn, we know that that cannot be true. And if it's not true, then its opposite has to be true. Okay, so we're going to try two more. All right, given triangle ABT with line CBTD, and AB is perpendicular to CD, so we've got a perpendicular line there. Write an indirect proof to show that AT is not perpendicular to CD. Okay, so that's our indication again to use the indirect method. So I'm going to, whoops, wrong. No, I don't want the highlighter, want the pen. Okay, we're going to have our statements, and we're going to have our reasons. So let's start off with what we are given. Well, we've got triangle ABT. We've got line CBTD, and we've got AB perpendicular to CD, given. The second step in your indirect proof is always going to be your assumption. So our assumption is going to be that AT is perpendicular to CD, or take that not out of there. And here's the reason. It's an assumption leading to a contradiction. Now, again, the contradiction is generally going to come from something that you were given. All right? Well, so let's follow. What do we do? Well, normally after perpendicular lines, we say we have right angles. So I'm going to call this angle 1, and let's call this angle 2 over here. Okay. So um, angle 1 and angle 2 are right angles. Well, okay. How do we know that? Well, because if two lines are perpendicular, then they form right angles. And they form right angles. If two lines are perpendicular, then they form right angles. Well, wait a minute. A triangle cannot have two right angles. So based off of these statements, we would have to say, in statement number 4, triangle ABT is not a triangle. Why? A triangle cannot have two right angles. Now, what did we do? We have a contradiction. Triangle ABT, well, I guess in this step it'd be better to say it this way. ABT is not a triangle. Get rid of the triangle part of it. That's a contradiction. Well, how did we get to our contradiction? We got to our contradiction from our assumption in statement 2. So once you find your contradiction, the last step is to say what you're trying to prove, which is AT is not perpendicular to CD. And the reason for that is contradiction in steps, okay, 1 and 4. So again, you assume the opposite of what you're trying to prove, and then you try to find a contradiction. And once you find a contradiction, you're going to give your proof statement and contradiction in whatever steps you found the contradiction. Okay, so we have one more that we're going to do related to that. Given trapezoid rows with diagonals RS and EO intersecting at point I, prove that the diagonals of the trapezoid do not bisect each other. So here's what we're trying to prove. The diagonals of the trapezoid do not bisect each other. Again, it's the word not that tells us let's use the indirect method. Okay. And this one isn't going to be all that long. There's probably different ways to do this, but let's see if we can find a solution. Okay, so number 1, we've got trapezoid rows, ROSE, and with diagonals RS and EO. Start out with your givens. Okay. Second thing that you always do is to assume the opposite of what you're trying to prove. So in this case, it's going to be that RS and EO bisect each other. And the reason is an assumption leading to a contradiction. Again, okay, assumption leading to a contradiction. Again, we're making a turn in the maze here, and we got to know, did we make the right turn? All right, now, in this, if RS and EO bisect each other, this would have to be a parallelogram because that's a property of parallelograms. So we could say ROSE is a parallelogram. And the reason is if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Now, we need to remember from our discussion on parallelograms or quadrilaterals that a trapezoid and a parallelogram are never the same. So we've got a contradiction. All right. This right here is a contradiction. You cannot have a trapezoid. A trapezoid does not equal a parallelogram, ever. Okay. They're in different categories when we did our flow chart. So now, how did we get to statement 3? Well, we got to statement 3 from statement 2, which means we made a wrong turn. And therefore, RS and EO, okay, do not bisect each other. And the reason is because of a contradiction in steps, okay, 1 and 3. Can't be a trapezoid and a parallelogram. All right. So again, couple keys. You're looking for, when you're doing indirect proofs, you're looking for not. You have to prove that something is not true. When you have to prove that it's not true, step 2, after you bring in your givens, it's going to say the opposite. And the reason, an assumption leading to a contradiction. And then build an argument so you get a contradiction, and therefore you made the wrong turn. So what you're trying to prove is true, and the reason will be a contradiction in steps, and whatever those steps were that you had. All right, so good luck with that, and we'll do some more of those in class, and this will be the end of our units for the year. Well done. Bye.